So that's a clip from Cannibal the Musical. I felt like this was a really appropriate thing because we're doing front end, which is definitely kind of feels like a frontier right now. And we all think we know precisely what we mean, but I don't think we do. So I'm hoping to help with that problem. Oh God, it's gone back to super small mode. We might have to live with super small mode. I'm sorry, guys. Or wait. No, I do. I still have the regular size. Hooray! So this is a library that I'm still writing and putting together, but does work, and you can use it now if you want to. It's written in Haskell and uses JSAddle. You guys familiar with JSAddle? Who knows what JSAddle is? Okay. So JSAddle is a project by Hamish McKenzie that binds to the type specification of the JavaScript APIs and automatically generates Haskell bindings for those APIs. Now, the interesting thing about JSAddle as a library is not only is it complete code generation, or almost entirely code generation, it allows by code generating that allows an abstraction over the way in which this code is actually executed. So for example, there's a project JSAddle Warp, which uses Warp, which is a web server for Haskell, to serve an HTML page, and then actually executes your Haskell code on the back end in GHC and sends commands to the front end over a WebSocket to be executed on the front end. So your front end code is actually running on the back end and communicating changes over a WebSocket to the front end to reflect the types of I/O actions we're doing on the front end. So you can think of it like the front end becomes an RPC call, sort of a thing. But because we have this universal abstraction with JSAddle, you can take that exact same code and use GHC.js, which is a Haskell to JavaScript compiler, and run that same code there, produce a JavaScript artifact, and have the same actions, the same effects, right? And now we're having web GHC and the other one from Twig, I can't remember the name off the top of my head, that are WebAssembly projects for Haskell. And those projects as well work with JSAddle. So if you can compile it to something that we can interpret from JSAddle, you can run it. And JSAddle allows you to run JavaScript things. That's specifically the space that it's in, right? Like if we wanted to control an iOS application's front end or JDK or something else, JSAddle doesn't do that. It does JavaScript things. Actually, it might do JDK because I think that's in JavaScript now. But that's not something I know about, right? So by using JSAddle, you can see that just imported here, we get these properties. And so what I've put together so far is the core abstraction, which is what I really want to talk about, as well as several add-on libraries on top of it that make it actually work in real life to build an application. And I'll show you some examples that I put together, including to-do MVC. So you can get a sense of like what this code looks like in actually doing something. So the core abstraction here, Spadoinkle, is just this one file. And everything beyond this is a plugin. So this is the one file. And that's the whole thing. So this one kind of central piece of specification logic should allow us to write front-end code that can be executed on a variety of different interfaces. At the moment, it successfully executes with JSAddle Warp and GHC.js. But there's no reason that we can't write this in PureScript if we want to use PureScript things, or JavaScript, or Swift, or something else. The abstraction is universal. So I'm going to walk you through a little bit of what this actually looks like. So I should not have called this HTML, but hey, this thing still has negative entropy. So this data structure here is basically it, and right now it represents HTML. We could advance this and make it more abstract, but right now it represents HTML. So as representing HTML, it's a GADT, and it only has two constructors, one for text and one for nodes. And so any type of a UI that we can represent as a tree should work with this in theory. Oh, hey, Alex. He's going to go around the other way. Pacing, everybody. Okay. So this one data structure is universal to all the HTML we could ever need to render, and it has a substructure of prop. You see in there prop? I believe I have prop defined down here. Yep. So prop is also very simple in that it has just the three constructors. It can be textual, it can be a listener, or it can be a bool. Basically, it's a sum type with those parameters. And the nice thing about this is, so let's talk about the type arguments to HTML. That's a better place to start. Like I said, I did no prep whatsoever. So the first type argument is a type to type. So that can be a monad or a functor or whatever you need that to be. And the second one is already a type. So if you're not familiar with this you can replace type with star. It'll do the same thing. This is just kind of a more modern notation for it in Haskell. So with that, when we see these HTML of M, O, the M is likely going to be some monad in which we would like to do side effects, in which we want to do stuff, which things need to happen, right? We want to make an XHR call. We want to fire some missiles. We want to, deploy SEAL Team 6. I don't know. Some very intense I/O action, I'm sure. Definitely not incrementing a number. And we have the same type of arguments on prop, and this is the only place O actually gets used. So you can see that listeners are a function that returns an M of O. So assuming that M is some monad, then that M can fire the missiles for you, right?
O is what?
O is what? O is whatever that monad is going to return, right? So it's an M of O. So imagine M is I/O, right? So that means listeners are taking a raw node, right? And this right now the library is just for HTML. It won't be in the future, but at the moment it is. So it takes the raw node that this would be the target, like event.target in JavaScript, right? The raw event, that's going to be the raw JavaScript event object. And then you do something with it, right? Then you return an O. So you produced something. And so all of the HTML gets typed to that O, right? That output of the HTML. And the only time that O is ever used is in listeners, right? So everything else is completely pure. This is the one location in which you can do side effects, right? There's nowhere else to do it. It's just a data structure. It's not a monad. So because of this, and I just derive it here, HTML of M is a functor, and that's it. It is not applicative. It is not a monad. It's not recursive. You can't combine them in any way other than map. It's just a functor. And this is a virtue because it means that we cannot have sequential view logic. The logic all has to occur in the context of some action that the user's taken. We can't do things like have complicated recursion, or if you've done higher order FRP, you can end up with these like causality loops where this part of the model, this part of my view depends upon this output from this part of my view, but this part of my view hasn't outputted anything yet. And so now I have a non-terminating program and my life is painful and horrible and awful, right? So by restricting this to being just a functor, and it's naturally just a functor, you cannot write an applicative instance for this. But by having something that's just a functor, you're guaranteed non-sequentiality, which means not only is your code going to be hopefully simpler and easier to maintain, but we can potentially execute each part of the view in parallel. Does that make sense why that's the case? Okay, cool. Hey.
Suppose that we do need to do some monadic things.
Yes.
Would that node be outside the scope of any specific monad?
That's specifically the M that we have here. So.
Oh, okay.
Oh, good, the RoboKiller got it. So that M there inside of prop, this one, that's where you can do that. That's the only place inside of Shapiro that you can do that. Now, part of the idea with this library is that the library is not doing very much for you. It just gives you this programming model, right? So how you use it is really up to you. So that M, right, that could be a reader, like a reader T transformed monad that's got some environmental context in it that might include FRP streams, right? It's really up to you what you're doing with that. You could put a state T on there and have stateful computations in your listeners if you wanted to. It's not opinionated about how you use it. It's just providing you with this very, very simplistic programming model that has what turns out to be like a huge degree of polymorphism, where you can take code written in this model and execute it against a whole bunch of different contexts. So it's just giving you this like very, very simple core, and that's all that this file is. This file is all that Shapiro really is, and beyond that, it's all plugins. So we have some. Oh, sorry. Go for it.
The one thing with the functor is how are your components work? You can't do self-contained application, self-contained state, right?
Correct.
Just like in the Elm.
You cannot do self-contained state. That is absolutely correct.
Okay.
You cannot encapsulate state. That is not allowed. So if you're familiar with like the Redux model or Elm or Spork or some of those other things there, you have a central source of truth that represents the truth for your whole app. That is also necessarily the case. Right?
If I wanted to write an app that did have self-contained state, I would need to write a separate one of these apps and find a way to embed it opaquely inside of.
The whole idea is that you don't do that. Like part of the idea here is that that's not something you want to do. It's something you might think you want to do, but you kind of don't. The benefits of a single source of truth are overwhelming in front-end programming, at least in my opinion. If you start having multiple sources of truth, which that does, like if you're like a React developer, that's like the equivalent of using set state somewhere inside your program, right? So you want to avoid that. And this model restricts you from doing that. You can't do it. You're just not allowed.
So what type of apps is wrong for using this for?
I mean, you can write, it's a way, right? It's a way in which you can write a UI. It's the way that I'm currently suggesting to you all that UI could be written. I'm not saying it's the way that you want to write it, right? Like, you might not like writing it this way, but I've yet to find a conceptual case where this becomes awkward. And so I'll show you kind of how components work in a moment. Because you still have components, right? You have code reuse. You want to reuse the logic from this component over here. We definitely support that in Shapiro, but we don't support encapsulation in any way. So if you want to have, n things on screen with the same model, you're probably having a hash map. Where as those things are being spawned, they're getting an ID, and so they can refer back to themselves, this type of thing.
Okay.
But it's definitely doable. But other thing to keep in mind is that when I say you're restricted in this way, excuse me, you're restricted in this way only in regards to state that your view depends on in some way. You could have something else inside that M. Your view can't depend on it, but you have access to it in listeners. So you can have yet more state that doesn't fit this restriction. Excuse me. That is awful. Okay. So this is based on these two type families. These are the two type families that make the system work. Geez, I'm really sorry. The first one is Shapiro. Shapiro has an associated type family, vnode. Vnode is your backend. So a Shapiro is essentially some context in which we can execute Shapiro code. And we need to know what type of virtual DOM, virtual UI implementation you have, which is that type family. Oh, thank you, Cameron.
One open bottle of water.
Much obliged. The functional dependency there is just to make things decidable. Hasn't gotten in the way yet because you're only using one backend at a time. If we're trying to use more than one backend, I can see that functional dependency getting in the way. But it just makes things decidable. This associated type is how we represent the virtual DOM or some UI data structure. And then we have these three methods. The first one is how do we interpret it? To interpret it, we need some way of going from your monad with a natural transformation to JSM. So this has to be natural. By that I just mean it has to be polymorphic, right? So for all M of A, JSM A.
What is JSM again?
Okay, so JSM is the execution context for JSADL. So JSM is like the IO monad, except if it's GHC.js, it's the IO monad. If it's GHC, it's a separate monad that sends messages to the browser to be executed over there. It's kind of the universal execution context monad for the UI. So you can think of it just like it's the IO monad. It's just JSADL's version of it that allows for this multiple execution context thing that Hamish McKenzie built. So we need to be able to go from the monad we have that we're supplying to our app to some way of executing, doing some work, right? We take in some HTML. B is the backend. We're parameterizing basically this, just the B here. That's all we really care about. And then we return that same backend with virtual DOM. So it's saying, I need to take my data structure, my Shapiro data structure of HTML, and convert it, probably while doing some I/O action, into the virtual representation for this particular backend. The next one is patch. This takes a raw node, which is going to be where this thing is going to get rendered on the page. Maybe a virtual node. So if we're in the first execution, this is nothing. Otherwise, we have a previous execution to diff. Diffs it against this next data structure, and then returns a new data structure. And then we have setup, which is just a convenience that you can do something to make your backend go prior to running the app. So let's say your backend is React. This would be where you'd set up whatever React stuff you need for your backend. I'm sorry. A should be O. It's the O from up here.
Okay.
Yeah. I abstracted out the state management system as well. So you can power your Shapiro app with a reflex stream or a Streamly stream or a conduit or whatever you want, or you can use the very, very simple primitive of a tvar, which is one implementation I have here. So got the one implementation tvar, and then here's actual Shapiro, which I'm going to gloss over and go over really, really fast because I want to get to more fun stuff. So this is the entry point for all Shapiro apps. We build up a larger natural transformation from our back end of M to JSM. We have this little infinite loop here, and we run our setup. We run the setup from the back end, find the stage, which is where we're going to be showing our app. We do our first interpretation of the model into our data structure. We execute this if we think there's a change, and we have, and then we patch, and this patch will actually do the rendering onto the screen. And so this go thing uses should update, which should be infinite. So if we look back up here, the semantic of should update is it should run this function every time we think we need to update the view. So whatever semantic you have for doing that. Usually it's just equals. So far this is all I've ever needed is EQ. So as long as we can compare models to models, we can know whether or not the model changed. So far so good? So let's skip over the rest of the technical stuff and actually look at some code. All right, so this is my little minimal counter example using this. This runs, like I said, on both sides. And that's it. That's the entire thing. This is the view for the counter, and this runs it. I'll give you guys a second to look at that and ask a question if you have a question. Everyone see how that works? So this is the kind of the paradigm shift that I experienced, and I'm trying to socialize. In writing lots of Elm and halogen and different stuff in functional UI, there's generally a need to couple some location, right? We have some location in the DOM that we want to show data, and we want to couple some location in the DOM where the user is going to interact, or we want to change the model. And it appears to me that all of the front-end, FP front-end systems are describing ways of mapping these things together. If you're doing higher order FRP, then you have some kind of a click listener. That click listener returns a stream, and you wire that stream through some FRP network that transforms data around, and you also wire that network into like text nodes on your DOM to update the view with the state of that stream. Right? That's like one way to do it. Another way to do it is like the Elm architecture, where we have a type representing this mapping. We have this message type. Right? This is also true in Redux. We have this message type, and this message type is this big manifest of all the different messages that the user might do. And then we have another central place in the code where we map those messages to our model transformations. And then we have another place in the code where we describe the data structure of our view, and we say, all right, here's where we're going to map this place in the model to the view, and this is where we're mapping the messages that are going to go back up and transform the model, right? So there's a lot of ways of describing this. And the thing that I realized is that the absolute simplest way of doing this is actually the super, super old school way. A long, long time ago, before there was jQuery, we attached attributes directly in the DOM. We had onClick, and then we used JavaScript : and then named a function, right? And as long as that function was in scope somehow, it ran, right? And we didn't really have a good way of binding data into the view, but at least we had this very good way of mapping changes to the model from the view, and we had some kind of global mutable state. Well, I actually think that was the right way. We just kind of got really lost on how bad it was in practice to do that in a language that's highly mutable and full of pitfalls, right? So we tried to escape that. And this is actually what we have here, right? We're taking in as an argument to this view function the current model, the current count, which is an int. We display that here to the user by showing it and making a text node out of it. And then on our button, we have this onClick prop where we respond with a new version of the model. And so by doing it this way, the idea is that we kind of don't have all the boilerplate. We don't have this message type that describes this mapping. We don't have this one giant central function where we take this mapping and show how we're going to change the model in response to this mapping, right? Instead, we have this very direct programming model where we say what we wanted to do to the model right in the location where we know what we wanted to do and nowhere else, right? And there isn't any reason that we can't move these logic pieces out and move them up to the top level, which is what I'll show you next. Does that make sense so far? Okay. In addition to things getting randomly tiny on me, I also can't see on the screen because I don't know how Nixos is supposed to work with the projector. So this is 2to MVC. Sure.
It's a special type of thing that will cause the JSL to re-render over WebSocket.
It depends on how you're executing it. It works no matter how you execute it. So, for example, So like if we go back here, you'll see I have these C++ things in here. So if it's running in GHC.js, so it's running in JavaScript directly, this one will get used, which will just run it in GHC.js. And if we're running it with JS out of warp, where we're communicating over a WebSocket, it'll use this one, and it'll serve the view on port 8080. Right? Because now you need a server, because it's not producing a JavaScript artifact, it's producing a server, right, that communicates over WebSocket. So it works either way. And then, of course, up here, because I have things like redundant imports cause me to not compile, I have to put it here as well, because we don't want to import the warp server if we're running in GHC.js, because you can't have a warp server in GHC.js. It's just not an execution context where you can run a warp server. You need GHC. Sure.
Yeah, I'm not familiar with the WebSocket thing. What gets sent to the WebSockets? The function count +1 gets sent to the server?
So if you're running this in a WebSocket context, if you're running this with GHC on the back end, then all of this actually that you're seeing here will get executed on the server. The only thing that won't get executed on the server is the output of the virtual DOM differ. So when the virtual DOM is diffing and saying, here's the stuff that we need to do, it'll send a minimal set of the updates over the WebSocket, where there's an interpreter written in JavaScript by Hamish that will take those instructions and go, let's execute the JavaScript IOs to make the necessary change.
Okay.
So you can do it either way. JS out of warp is not for production. Do not use it for anything other than a dev tool right now. It's just not strong enough for production. The GHC.js version is absolutely strong enough for production. I don't have a problem putting this code into production through that path today. Okay, so I wanted to take a look at 2.2 MVC so you get a sense of what this looks like powering like something more substantial as this program model looks like doing that. So here we have just the view. And this is actually runs on both as well. And this is I do have a complete implementation. So it supports local storage and all the spec. So if we take a look at this, let's just kind of unwind it a little bit. You know, here we've got our to-do list, right? And we're going to take in a model, and we return an HTML of the same model, right? Because that's the programming model for Shapira. And we can see in here that we are just executing this little function. We're taking some fields off of the model to determine what's visible. This is filtering the tasks that are on the model. If you're familiar with 2.2 MVC, is filtering the tasks that are on that model to the ones that should be currently visible based upon the filtering settings that the user provided, which is this visibility field on the model, and then just f-mapping over that, f-mapping over task view, and putting it into a UL. And that's it. That's all that's necessary to accomplish that. Let's take a look at task view, because I think that's one of the more complex ones, yeah. So here's task view. So task view takes a model and a task and gives us back an HTML of model. And we do need to do some actual I/O here. So that's why this M is constrained to monad.jsm, because we're going to do real stuff. So is all this making sense so far? We have these classes that are optionally there based on these predicates. We've got our input. On click, we remove task, all this type of stuff. So this is just the view. And one thing to note that's different here versus the counterexample is the counterexample, the plus and minus operators were inlined into the view. There was no like controller layer, update layer. There definitely is here. I've moved that out. So let's take a look at what the updates look like. So as opposed to, just keep in mind like what you're used to with like Elm architecture style functional UI programming or FRP, and then take a look at this. So this is the controller layer or the update layer of the 2.2 MVC app, and that's the way it's written. That's the way it looks. So as opposed to having a giant update function with dispatching, and I'm going to map these messages, this thing, and all this type of stuff, instead we just have functions. We have functions from model to model. And so this allows us, if you want to get fancier in your thinking, but actually it's not so much, this basically allows us to think in the monoidal category of model, where the object is model and the arrows are functions from model to model. And so if we look at something like toggle complete, this toggles the completeness of tasks, right?
How we deal with premises?
Beg pardon?
How we deal with premises?
I don't understand the question.
I mean, there's the UI, reactive and asynchronous, right?
Yes.
So you click the button, and then at some point in time, it will return you something to update the model. How we deal with it?
You're talking about asynchronous programming. It's an M of O, so however you normally do it is fine. Right? Like that M is whatever monad you want. So if you want to use, let's say, async, the async library, and you use concurrently, the concurrently monad, you can do that.
Where is the M here? I just see model.
There's no M here. That's kind of my point. All of these are pure.
Okay.
All these are pure. Now, you could have an M. Like we could, if we want to do some I/O stuff, we can do it in here. But in practice, this is usually the way it comes out. The update layer ends up being completely pure. In the case of to-do MVC, we don't need to do any I/O in the update at all. We can handle all of that outside of the Spreadwinkle app. And so as a result, it's completely pure. And we get nice properties like toggle completed becomes one arrow in the monoidal category of model for each task ID. Right? So for each task ID, there's one arrow in that category because task ID to model, right, is another way that we can represent this. Or toggle all just becomes an arrow. And so all the boilerplate of like connecting this stuff together goes away. So let's take a look at, for example, remove task. So remove task here gets called over here, right there in the onClick. And so that's the connection. Instead of having a message type where we send it and we have to capture it and move it back, we just reference it directly in the view. Hey, when someone clicks on this, remove that task. That make sense?
Can you go over, like, look at, for example, the definition of what an event handling like on
Yeah. Let's see if I can, if my Vim skills while not looking will work. Let's see, so, so take a look at, I'll give you guys a second to digest that little piece. So one thing to note is that all of the event handler functions, these guys, have two flavors. A flavor that we're seeing here without the prime, which is basically taking the result and passing it to pure. So that gives us the M, right? So that M must be applicative to use the non-prime version. If you use the prime version, then it's whatever M you want. And so that's when you would do, like, I'm going to fire the missiles. So yeah, if we wanted to do some I/O inside of update task description, we would end up with an applicative constraint on the top there, or a monad JSM constraint rather, sorry, of M, and then we'd return an M of model. And over here in the view, we would use on input prime, which doesn't pass the result to pure. It's expecting an M. Okay. Make sense so far? All right. And so this is the last file in here for the to-do example, and that's the types. And so I hope you can see kind of why I think that this might be a powerful model for doing UI programming, in that there's just not very much going on, and we have a full 2 to MVC spec. Originally, when this was one file, and I didn't have like so much white space, it was something like 200 lines of code. By contrast, like the React example is like 8 files. Each of them are quite intense. So like, and that's actually the simplest that I'm aware of out there in JavaScript space. Like looking at the different examples that are there, I think React is the best over in JavaScript space, as far as the 2 to MVC example goes specifically in this context is what I was looking at. So yeah, there's just not very much. We have the 2 new types for description and task ID. We've got complete versus incomplete. We've got visibility for those visibility buttons, a task, a model, and I provide an empty model to be the initial state. And it all just kind of gets wired up. So here where those pieces just fit together. Now, you asked about components. So let me show you an example of a submodel, right? So this is, it's kind of weak, but this is my one component example right now, is this filter HTML. So this is the footer of 2 to MVC, where you click a visibility like all or completed or incomplete. Familiar with the example? So this filter HTML, this is one button, one of those 3 buttons, right? So this is the code that generates one of them. And so in here, this represents like a full submodel. So we have a visibility. The first visibility represents what the current visibility of the app is, right? From our state, from our parent model. And the second one represents who am I? What visibility am I? Am I the all, the complete, or the incomplete? And then when I'm clicked, I'm just going to fire myself, right? When you click the all button, it just fires an all back into the ether. And so here we've got current item, and current visibility, and the one that we are, the item that we are. On click, we fire the item that we are. And if the current item and the item that we are the same, then we have a selected class. And the text for this button is going to be showing the item, right? So this is like this little subcomponent that is not stateful, but shows like a submodel, right? We have this like smaller thing. We want to embed it a bigger thing. And so where does this get used? I think it's in the list footer. Let's search for it. There it is. Okay. So the part of the purpose of this particular example is to be illustrative. This is not the way I would do it. But all we need to do to embed this, filter HTML. So here we have filter HTML. We pass it in the visibility from the model. And then we pass in, we map over this all of the visibilities. So min bound, max bound, it's a bounded enumerable. So this gives us a list that's automatically all complete, incomplete. There's only 3, but this is more fun, right? I could have supplied all 3 manually, but this is more fun. So that makes a list all incomplete, all complete and incomplete in a list, in that list there. We map that over filter HTML, which will give us back a list of HTML of M of visibility, which is not our model, right? So all we need to do is fmap. That's literally it. The mechanism of embedding is fmap. So here with fmap, we embed this in by taking the visibilities that are produced by the component and placing it onto the parent model, which will give us back an HTML of model, right? So as long as we have some way of going from the parent, going from the submodel and the parent model to the new model, a setter function, then fmap is all we need to embed. So far, so good? Okay.
Yeah, I recall writing something in PureScript,
Yeah.
Elm style, where you have the manifest of all the actions.
Mm-hmm.
And that was one of the hardest parts about doing the child components.
Yes. it composes by brute force. This version composes by fmap. Because,
That's pretty attractive.
thank you.
You're attractive too.
All right. So that was my 2 to MVC example, and I hope that shows like, hey, this actually works in real life and produces extremely simple to reason about code, and is open-ended enough that it's not standing in your way. If you want to have state T or reader T monad transformers on your M, if you want to have access to some giant record of mutable variables or streams or some other asynchronous abstraction, you can have that. If you want to do asynchronous programming, you just use applicative or however you normally do it, because it's not going to stand in your way. All that it enforces upon you is HTML is only a functor. And this is how you embed it, and it deals with the wire up for you. And all the wire up to make all this work is just this one function, this little guy here. That's it. That's all that's necessary to get the model to be heard from the user, be reinterpreted, diffed, and re-rendered. It's the whole thing. So
when you say that the model is,
I'll go for it.
when you say that model is a functor, that's from the category of model to the category of HTML of that model?
No, HTML_M is a functor. If I said model is a functor, then I misspoke. HTML_M is a
I
functor.
probably misheard that.
Oh, no problem. Yeah, HTML_M is a functor. This thing. This bit is a functor. From Haskell to Haskell, it's a normal Haskell endofunctor.
Okay, because like I imagine that a list is a functor
from Haskell to Haskell.
Okay, yeah, okay.
Yeah. Yeah. So, what's up? Yeah. Yeah. No, I'll show you it running. The reason I'm not, I'll do it, but I'm scared that if I kick my machine wrong, it will go back to tininess mode. So let's see. I think it's. So this is just hosted by GitLab. So here's a 2 to MVC. So here's that filter HTML, controlling what we see. Oop. Ta-da! So that's that. Now, what I showed you is actually not the code that this produces. What I currently have hosted right now is a slightly more advanced version, which I'll show you next, if I have time. Or how am I doing on time? I'm just kind of going for it. Oh, we're doing fine. So, yeah, that's that, and so that does all the wire up necessary there. All right. So the next thing, since we do seem to have time, if you guys want to see it, is the work I'm doing now on this, which is about. I know what I should show you. I'll demonstrate this multiple backend thing. Okay. So if I go to 2 to MVC here, the main down here is running Shpdwinkle with run pardiff. So pardiff is a somewhat parallelized virtual DOM written in Haskell. Okay? And by putting run pardiff here, it will execute this Shpdwinkle in terms of pardiff. And so here is pardiff. So I'm not going to go through all of this because this is a bit more intense, but this is the virtual DOM implementation. And I'm using alignable functors to do the diffing for me. So everything is just a data.align. And then how do we respond to that? Turns out that JavaScript is very crappy about certain properties. They don't all work the same. You can't just delete checked and expect a checkbox to no longer be checked. You have to set it to false, this type of thing. There's the patching, all this, and the purpose of this implementation is to serve as canonical because we don't have to use it. So here's a much faster implementation that uses a JavaScript library that I didn't write. And so this backend will execute exactly the same 2to-MVC code, but we'll execute it using a library called SnapDOM, which is a very high-performance standalone virtual DOM library written in JavaScript. So you can execute it how you like. Now, obviously, if you wanted to run this on the server side and use the WebSocket path, you might have some reason for using the pardiff because you think it might be faster in your case because of parallelism, but probably not. The multiple backends will work regardless of whether you use it from the server side or the client side. If you execute this in GHC.js or execute it in GHC, both will work exactly the same. It's virtually no different. You can still use the JavaScript native virtual DOM library. And so this just binds out to that library, and we embed this setup.js file in our setup. And so, there's setup.js. And so that pulls in SnapDOM in kind of a hacky way.
Or is this something you wrote?
This file?
Yes.
I wrote this file. I did not write SnapDOM. SnapDOM is an off-the-shelf component. So I'm trying to show you guys that, like, let's say, and this is actually a pretty serious advantage because there's always advancements going on in the way in which we might render a virtual DOM. And so if we have this single Shapiro specification to represent a universal truth about UI as a data structure, then we can use more than one backend. And we can even write the same app and go, I'm curious if this renders faster if I use the React backend versus the SnapDOM backend versus the incremental JS backend versus the native backend, right? And you can just change it out literally with just this. So, yes, absolutely. I'm even going to demonstrate that it works. So here is with run pardiff. You'd think so, but GHC.js has a cost. It's about twice as slow. Now, granted, by twice as slow using the pure Haskell implementation, we're still faster than React. Believe it or not, this thing actually performs, which is something at the moment I think I can only say about this in GHC.js. I'm not aware of anything else in GHC.js that performs. There's probably is something, but I'm not aware of it. So let's see. And that's like by my opinion of perform and all that, caveat. So this is another implementation of 2to-MVC that I was playing with. And this one runs in SnapDOM, and that's virtually the only difference of main. So depending on what function you pass there, Haskell's type class system will determine everything else about the system based upon the type of that function. So because that function is of type SnapDOM T of M, it will do the whole thing for us and allow us pluggable backends and pluggable rendering layers via the one argument. Cool?
Have you tried to import other JavaScript components to use as if they were DOM components?
No, and I'm not even sure that I can just yet. I would like to. I have a model in mind that I'm calling Potato that does that, but I don't have that right now. Right now, Shapiro is a closed inductive system. So you can embed Shapiro in things, but you cannot embed things in Shapiro. Now, I'm just wanted to demonstrate that that's how that works. And actually, the 2to-MVC that we just saw is using the SnapDOM backend. GitLab will only give me 1 GH pages, so I couldn't host both versions. And I'm not going to try and get it to build right now while not being able to see my laptop. But it does in fact work with both backends. With the SnapDOM backend, we actually outperform Elm 16. So we don't outperform current Elm, but we outperform older Elm, and we way outperform most of the JavaScript frameworks. As by sheer virtue of it just not doing very much. Shapiro is really, really, really simple, and by virtue of just not having very much code to execute, it goes pretty fast.
What animations?
You could definitely do animations, though I haven't tried animations outside of CSS animations yet.
Right.
But you absolutely could. You could do animations here. So like one way that you could do animations is you'll notice that we build some kind of a model before we pass it to the Sprunkel function. So let's, for example, say that this model is a stream. Let's say it's a reflex stream, right? It's a dynamic reflex stream. If it's that, then now you have a way outside of Sprunkel to drive your Sprunkel app. So changes made to that stream outside of the Sprunkel app will be reflected, right? Let's say you use a tvar, which is all the versions I have here are using. If you're using a tvar, then there's nothing to stop you from making changes that tvar outside of your Sprunkel app. It'll just reflect. Sprunkel will detect changes to the tvar and reflect it on the page, right? And if the Sprunkel app is making changes to the tvar, you can listen for that outside the Sprunkel app as well. So if you can listen and send messages in both ways, then you have all the properties you need for higher order reactive programming outside of the app. So now you can puppeteer multiple Sprunkel's that way. You could have a reflex DOM application and use this as an optimization for only certain parts of it. You really have control. So if you want to do animation, you could do something like, say, I'm going to set an infinite loop using JSAddle that fires on request animation frame. And every time we request animation frame, I'm going to execute this model update function that updates the model in some way to reflect that animation, and that will just drive the virtual DOM. You could have no I/O. It could be a totally pure view. So all you're passing to Sprunkel, not using its state management at all. It's just rendering out whatever you sent it from outside of Sprunkel. So that's totally allowed. Another thing that's kind of nice on like one project that I'm working on where I'm using the JSAddle warp backend is if you use that backend, then that M can actually be I/O, meaning you can be hitting your database in there, right? So now on click of this, here's the SQL to execute. It's one programming context for both the front end and the back end simultaneously. You can do nice stuff because it's not opinionated. I want to talk about this version of Tudo MVC because I think it's interesting, and then I'm going to shut up and go away. So when I was working on this, I had a friend who I showed this to, and their response was, does it optimize when to recalculate the virtual DOM? Because this is an optimization that's really common. React has this in should update. Elm has this in html.lazy, which should be called html.memoize. It has nothing to do with laziness. I don't know why Evan is such a jerk. But that's the case, right? We want this thing. So I wrote a little memoization function and put it all over the place, and then excitedly checked my preliminary performance measurements and rubbed my hands and for the satisfaction to come, and it did not show up because all of my pieces are taking model as an argument. So if we memoize with the size of 1, we never ever use our cache because the model isn't equal to itself, right? If something changed, there's no part of the page by which the model didn't change, so we never use the memoization. So we just eat memory and for nothing, which sucks. And so that's disheartening and made me go, maybe you know, what are we going to do about this? Because this is a really important virtual DOM optimization to be able to cache a computed view, because you could have expensive stuff going on in that view. You don't want to compute that every time the model changes always. That's not going to work. That's not going to work. And I had this beautiful idea where we go from model to model, and it's not going to work because we can't memoize. So I started working on what can I do about this. And I have an answer, and my answer requires no changes to Sprunkel whatsoever. So I hope you'll like it, but this is the answer to that question. So the answer to that question is to subtly change the nature of our view to, instead of taking model as an argument, we return a function of model to model. So now toggle all button doesn't take any arguments at all. It's just a list of HTML that returns functions of model to model. And that's now the case with quite a lot of this code, right? So now we can memoize. And so I have this polymorphic thing memo that uses type classes to deal with variaticness. It will give you a variatic function. So this one will memoize all 3 arguments. This one over here will memoize the 1 argument. It's the same function. So now we can memoize these 3 things, and if any of these 3 things didn't change, we don't recompute. Now we get that optimization. And we get that optimization by returning a thing of type model to model. And so we might go, okay, well, this is great. So now HTML is like a compiler. Now HTML is like a compiler that's baking for us our transformations, right? Like here, based upon this view, what transformations should we have? And so how do we apply this? How do we actually use this in an application, right? Like we have these things of model to model. The render function is extremely clear that it must be render, right? That it's got to be from model to HTML model. It doesn't. I'm not going to change Spadoinkle fundamentally from the simple structure to a more complicated thing to handle this case. So it turns out that this is it. So this apply function here is the whole thing you need to embed these over, and all it does is it takes an A, which is going to be our model, and an HTML from model to potentially a different model, right? We're actually not restricted to be an endo here, and gives us back a B. And so here's how that actually looks in practice. So that's it. And so this example is using lenses to do the transformations for us. And the way the update logic looks is slightly different, actually. In that now there's actually less of it. So this is some weird experience I'm having with this project. Every time I find an optimization, my to-do MVC program gets simpler, and my UI library gets smaller. This has continued to happen, and I don't think it's done. It just continues to be the case. So by introducing this optimization, we eliminated a whole bunch of necessary updates because now there's nothing to do there. It's just the accessor function. It's now just the lens. And because the lenses are given to us for free, the size of the update space shrank by about 40% and is now just a little bit more sophisticated in that we have things that are not model to model. Now, too visible is task to task, list of task to list of task. So there's that. The types are the same. And that's it. That's my talk on Spadoinkle. That's the current state of affairs.